Now I'd like to talk about analyzing change scores. We've looked at repeated measures where we look at the trend over time from baseline to year 6. We could do repeated measures where we have axial length at baseline and then jump to 5 years and see if there's a difference. In this case, what we would be looking for is the interaction between lens type and year. We would if we look just at year, that would be collapsed across lens type and wouldn't tell us if lens type made any difference. And if we looked at lens type only, the main effect, that would just tell us if the average between baseline and 5 years was different. The interaction term says, does the change or does the repeated measure over time depend on the lens type that you're looking at? And that's like in that when we did the repeated measures even across all the years, that is basically the interaction term that is creating the significance of the difference between the lenses. Now that's actually not a very powerful way of doing it, and people prefer other means. One of those is analysis of covariance, which we've already covered. In analysis of covariance, you make everybody the same statistically at baseline, and then you look at you directly test their axial length at 5 years. And your answer will be in your original scale, so it'll be the millimeters of length of the axis, whatever. And so we want to, so it's convenient to have that. Then you have a direct comparison. But some people want to know, well, just how much did it change? Not just that there's a difference after so many years, but did it change? So rather than looking at the original scale of axial length, they'll do axial length change. Now this has a few more decimal points that are necessary, but if you look at 22.88 minus 22.73 is an axial length growth of 0.149. And so that's the change. So a lot of people just, instead of using the covariance, will use this change score. And there's actually nothing wrong with that, except that if people start in different places, then that change can make a difference. And so what people generally do not do, but they should do, is even though they look at this axial length change, they still put in baseline as a covariate. But the units that the analysis is going to be when we look at expected mean squares and such are going to be in this change from baseline to follow-up. And in our Moodle, we have a reference for this. It's a handout that's in Moodle, and it's Joseph Weiss, The Design and Analysis of Clinical Experiments, and he has a chapter on change. Okay. So let's do that. So we're going to analyze general linear model univariate. Now, we're going to, even though this is sort of like a repeated measure, we're not using the repeated measures. We're using the univariate option. And the dependent variable is change. And the fixed factor is lens type We can do lens type 2 again. But now we need a covariate, and the covariate is axial length 0. Now, even though axial length 0 is within this change variable, because this is axial length at 5 minus axial length at baseline. This is axial length at baseline. The change score does not make the adjustment of differences at baseline. It's this additional difference. So these two can still be correlated, and you want to eliminate that correlation, and you do that by adding the covariate. And again, we can go to options, lens type, and we can compare our main effects. Again, the authors like Bonferroni, but well, actually, I don't think Fleiss talks about this issue. I'm still going for the lens type. We can put in our descriptive statistics and our homogeneity tests. All right, so let's continue. Okay. And when we look at this, what do we get? Oh, we've still got our eyes split, which is okay, which we need to do, really. So again, this gives us our ends for our groups. They're the same. It gives us our mean differences. Let's see. Oh, these are the descriptive statistics. And then here's our Levine's test. Again, we have rejected the null hypothesis of equal variance, which is not a good thing. And we come down here and we look and we see actually axial length 0, the covariate was not significant. So technically we could drop this from our equation. You should still put it in. If it is significant, keep it. If it's not significant, take it out. And we note that lens type 2 has a significant difference again. I want to point out, if we look at this, let's say spheric versus growth, it's 2.15, the left eye. Spheric 2.13, slightly different. And not very different because the covariate wasn't significant. And that's what all those little A's refer to. And so these are, anytime we have a covariate, we're estimating the marginal means, and it does it by plugging in the values from the actual underlying statistical model. It doesn't do the raw statistical means and standard deviations like this does. It does estimates based on the model. And we can see our comparisons here. We note again no difference between aspheric and spheric, but a big difference between aspheric and those spheric lenses where there was growth. All right. So that's how you do change scores. The big thing with change scores are okay, but you should put in, or at least test, the baseline value. When you're doing a change from baseline, add the baseline as a covariate. If it's not significant, you could run it again without. You don't have to. All right. That's it.